Radio frequency identification, or RFID, is a modern-day technology that allows companies to quickly track and record the movement of items. Whether it is an assembly part or a finished product, as long as the item is tagged, then it may be accounted for using RFID technology. This eliminates the need for traditional manual methods of tracking and counting batches of material or product. Using Cal Poly's RFID Club, Polygate, as the basis of study, our team examined RFID tracking consistency. Consistency, in our case, was defined by the number of times, or count, that the tagged item was scanned. Ideally, an item should be read as many times as possible, so our experiments were conducted upon improving to this effect. This research, in turn, should aid companies on the proper way to use RFID antennas and tags, especially when transporting product in or out of inventories and warehouses. The antennas are connected to a receiver, which is connected to a modem that sends the data to a laptop using the software Alien RFID Gateway. The antenna will be identifying the test subject wearing a unique RFID tag as they walk through the gates from one direction. In our project, we focused on factors that may affect the capability of the antennas to read the tags.
Cause and effects. To study the overall quality of the RFID tags, we considered the different possible factors that may affect the desired result, consistency. After brainstorming several ideas, we decided to focus on the methods cause and test for the following factors. Factor A, antenna orientation, tilted or parallel. Factor B, passing speed, fast or slow. Factor C, coverage, overshirt or undershirt. Factor D, height of antennas, high or low. The gate testing may affect the number of scans due to the varying distances. Another factor our team considered was the speed at which the object or person passed through the two gates. When moving at a high velocity, the tags may not be easily identified or errors may occur. High speeds and low speeds were tested for this category. The placement of the antenna on the person being tested may also affect the reading rate. Whether it is about chest height or waist height, the distances also varied for this factor. This may be applicable to movement of large carts of material. A store may choose to place the antennas at the top of the cart or at the bottom. Lastly, we tested for the location of the antenna by placing the antenna on the surface of the subject's clothing versus clipped underneath this person's shirt. The concealment of the tags might affect the ability of the product to function perfectly, and errors in scanning might occur. Again, in industry, a company might consider placing tags on the inside of a cart or container if they would like it to be safely stored. Or if it was on the outside, it may be subject to more degradation, or it may fall off and be lost.
In our experiment, the effectiveness of RFID chips were evaluated by their ability to produce responses. Treatments that produced more responses were seen to be more effective in comparison to treatments that produced less. This equivalency is made because if the sample produces many responses when going through the gate, the probability that it will return no read on the next response is very low, assuming all conditions besides the treatment are held constant. We conducted 5 experiments, all with a sample size of 15. The base sample, or default sample, had our control attributes, and the following experiments had one attribute change depending on what factor we were evaluating. The default settings were chosen according to our knowledge about RFID to generate optimal readings from the antennas. The default setting had these 4 attributes: tilted, slow, over, and high. Sample 1 focuses on the antenna position, specifically tilted versus parallel. Sample 2 focuses on the passing speed, slow versus fast. Sample 3 focuses on the coverage of the tags, over the shirt or under the shirt. And finally, sample 4 focuses on the height of the antennas, high to low.
From the default sample, we were able to identify 4 factors that could cause a variation into the number of responses. As shown in the Pareto chart, the 2 most significant factors are position of antennas and passing speed. From our data collected, we saw that the orientation of the antennas being parallel in combination with going through the gate fast accounted for 95% of the losses in the experiment. ANOVA analysis performed for each factor show that there is not enough evidence to prove that the coverage of the tags, factor C, and the height of the antennas, factor D, affects the number of reads, and that at a 5% significance level, there is enough evidence to prove that the antenna's orientation, factor A, and passing speed, factor B, somehow affects the number of reads.
The conclusion from the ANOVA analysis can also be predicted from the variability chart for the numbers of reads shown in the slides, which shows a drastic decrease of the antenna's performance when the position of the antennas and the passing speed changed, and a minor change on the antenna's performance when the coverage of the tags and the height of the antennas changed. As you can see from the variability chart, the default setting generated satisfactory results for the specific RFID purpose, being a great reference for our projects. For the position of the gates, the tilted gates are found to be more reliable in scanning the RFID tag, but is also only effective for scanning the tag traveling from one direction. Further experimentation and a cost analysis could be done to decide whether having two tilted gates scanning both directions will be more effective than having one parallel gate for a system that requires identification for incoming and outgoing RFID tags. Controlling the speed of the flow of tags is also important in an RFID system. Having slower speeds would make the RFID system more reliable.